Hi, my name's Damien Arandt from the Testing and Commissioning Association. I'm here today at the Holmes Glen Centre of Excellence, where we're going to run through a brief introduction of VAV calibrations. When completing a VAV calibration, there are some basic tools that are required. These include cordless drill, micromanometer, pitot tube, hoses, calculator, tape measure, and your typical stationery. Although there are numerous items that can be used to measure velocity in a duct, such as a velocity probe or a hot wire anemometer, a pitot tube is regarded as the most accurate.
A pitot tube works by measuring the difference between total pressure and static pressure. Total pressure is the force pushing the air down the duct. Static pressure is the force pushing the duct outwards. The difference between total pressure and static pressure is expressed as velocity pressure. A typical micromanometer then converts this to velocity.
So why do we calibrate the VAV box? Systems are designed to have a specific amount of air delivered to a particular part of the building. In the case of a VAV box, an air handling unit delivers air down the primary duct. It's measured via a pitot tube at the inlets of the VAV box. The VAV box actuator then controls the air to the occupied space. Every VAV box has slightly different entering air conditions, and the K factor or calibration factor of that particular VAV box accounts for those differing entering conditions. It's vitally important that the BMS is a true reflection of the air entering that VAV box and therefore conditioning the space. This brings us to the importance of the BMS operation. It's important when you're calibrating a VAV box that you have full control of the BMS. Ideally, you want to be able to control the AHU operation, VAV set points, and of course the calibration or K factor.
First, the duct measurement is completed. In this case, the duct measures 200 by 200 millimeters. When marking pitot locations on square duct, we're aiming for a grid-like formation to ensure we are measuring an even cross-sectional area of the duct. We're aiming for a minimum of 16 readings, so we need 4 holes in the duct and 4 locations marked on the pitot tube. To get the 4 locations, we divide 200 by 4, which equates to 50 mil. Our first hole is half that distance from the edge of the duct. Half of 50 is 25, therefore our first hole is 25 mil from the edge. Our next hole is 50 mil past that, so 75 mil from the edge, and so on.
So we've measured our VAV airflow at 330 litres a second. The BMS is indicating that it's at 403 litres, so it's out of calibration. The existing K factor is 0.96. So to arrive at our new factor, we simply get our measured airflow divided by the existing BMS airflow and multiply it by the K factor. Once we do that, we arrive at a new K factor of 0.78. Now, at this point, it's really important that we retest the airflow to see that the new K factor is held and that it is accurate. So let's go and measure it.
We remeasured the airflow at 408 litres a second, with the BMS indicating 402. This is well within the typical 10% tolerance range. As such, we'd regard this as calibrated.
We now record the inlet static pressure. This is a handy reference for down the track if we're ever trying to diagnose problems. And it's now time to put our plugs back in and put the BMS back to auto. We hope you've enjoyed this brief introduction to VAV calibration. Special thanks go to Holmes Glen and AMCA for use of the facility. For more information on the Testing and Commissioning Association, please follow the links below and keep in contact with us via the socials.